Welcome to the lecture on solid solution strengthening and grain refinement. So, in this lecture we are going to have the discussion about the strengthening mechanism in metals using these two ways, that is solid solution strengthening and grain refinement. So, as we have discussed that if you talk about the pure metals, so pure metals are seldom used for the engineering applications, and certainly we try to have the incorporation of more and more atoms, type of different atoms which should be combined to have the better properties. So, what happens that most of the time if you talk about the solid solutions. So, in general the solid solutions will be offering the greater resistance to the dislocation motion. It means they have better strength as compared to the pure crystals. Now, that will be basically because of the stress field which is present because of the presence of these foreign atoms, foreign solute atoms. So, they will be creating one stress field because of different type of different factors, like it may be because of the size, I mean size may be comparable, or there may be change in the sizes. So, what happens that when you have the solute atoms, so you will have the presence of the stress field, and there will be interaction of this stress field with the dislocation movement. So, basically you require the large amount of stress to move the dislocation. So, solid solution strengthening is that by which basically when you do the solid solution strengthening, then the stress required to to move the dislocation will be increased as compared to the pure metals. And then the next thing we will discuss about the grain refinement methods. So, in that we will talk about that how when we do the grain refinement, when the grains are refined, when the grain sizes become small, so that that offers more resistance to the movement of dislocation. So, these two methods we will be discussing. So, so as we discussed that in case of the solid solutions, the stress field around the solute atoms interact with the stress field of a moving dislocation. So, you will have these two stress fields, and they will be interacting with each other, and then in that process basically there is a the greater resistance which is offered for the dislocation movement in case of solid solutions than the pure metals. So, basically when we talk about the solute strengthening, so that effect will be basically depending upon the two factors mainly. One will be the size difference between the solute and the solvent atom. So, they are the solute atom which we are using, and the solvent atom, I mean these two atoms are there. So, there may be the size difference between them, and that will be affecting the strengthening effect. And second is that the concentration of the solute atom. So, that these two factors are basically important. So, if you if you talk about the size difference, so if we see that if you talk about the effect of the size difference, so what happens that larger will be the size difference. So, the more intense will be the stress field. So, basically more is the size difference. So, that will be creating more intense stress field. Around the solute. So, the more is the size difference between the solute and the solvent atoms, more intense will be the stress field around the solute, and then in that case once they interact, then more will be the stress required for the moving dislocation. So, so that will be stronger interaction, and so more will be the stress required to move the dislocation. So, what happens that if you are if you have the larger and then the second factor is about the concentration of the solute. So, if you have if you talk about the concentration effect. So, with large concentration of solute, again what happens that the moving dislocation will be interacting basically with at many points, because you have that stress field. So, moving dislocation interacts with solute stress fields at many points. So, that basically that happens that when you have large concentration of solute, in that case you will have the moving dislocation interaction will be at more points, because the concentration has become larger, and in that case again your effect on the strength of the material will be there directly, because in that case the stress required to move the dislocation will be larger. So, if you talk about the these effects and try to interpret in a graphical way. So, if you try to draw the graph, so if suppose you are talking about the on the y axis you have yield strength, that is in mega Newton per meter square, and if suppose this is your atomic percent solute. So, as there will be concentration of solute as you increase, suppose this is your concentration. So, it will have 10%, 20%, 30% or 40%, that way it may go. So, this is percentage. So, what is seen in that case, if you are using the copper crystal, if you are strengthening this copper crystal by the other atoms. So, in that case if you look at, so suppose this is 50 mega Newton per meter square, you have 100 mega Newton per meter square, you have 150 mega Newton per meter square. So, what is seen is that the graph goes like, if you go for zinc, so and if you go for nickel. So, for nickel this is the graph. So, what is seen is for copper, if you talk about the copper. So, if you take the copper, its radius is about radius is 1.28 angstrom. So, if you have the other atoms are like zinc or nickel, which has, suppose zinc has 1.31 and nickel has 1.25. So, what you see that you have not much of the change in the, but certainly when you increase the concentration, you see that there will be increase in the yield strength of the material as you are increasing. Now, if you come to, so this is the showing basically the effect of the concentration of the solute. When concentration is increasing, in that case your proportionally your strength is yield strength is increasing. Now, if you took look at the effect when you are alloying with or making these solute atoms, you are adding like you are doing with suppose tin, whose radius is about 1.51 angstrom, or you are taking the beryllium whose radius is about 1.12 angstrom. Now, in these cases, if you look at these cases, what you see that for zinc and nickel, the difference is not so high. So, it is hardly 0.03 angstrom, in these cases. However, when the difference becomes more for beryllium you can see that it is the difference is about 0.16 angstrom, and if you see the tin SN, then it becomes even 0.23 angstrom, even larger. So, in these cases what you see that your strength becomes quite high. The slope of this line basically will be quite high in these cases, and that is why what you see that the difference in the strength is quite the yield change difference in the yield strength is becoming quite considerable. So, this is basically the effect of the change in the size. So, that can be seen that here you have the larger strength which is achieved when your size difference becomes larger. Now, if you look at the nickel or zinc, so what you see that in case of nickel and zinc both way you have the size difference is same. However, what you see that in the case of nickel the strength is more. So, that basically is depending upon the elastic modulus value of the nickel. So, for nickel the elastic modulus value is higher. That is why in this case what you see is that the increase in the value of the yield strength is higher as compared to when it is when the other solute which is present is the zinc. So, in that case you will have the more intense stress field in case of nickel when copper is with nickel as compared to copper with the zinc. So, that is why you will have the more strength in nickel as compared to zinc, even if their size difference is basically same. Now, what is important is that you might have the idea about the Hume-Rothery rules. So, what is seen from here that the size difference should be maximum as well as the concentration should be maximum, but then it means that you will get the best result when you have the maximum size difference and also you have the maximum concentration. But then both these conditions cannot be satisfied simultaneously, and that is in the line of the very famous rule, that is Hume-Rothery rule, and that tells. So, your Hume-Rothery rule basically is giving you a limit on these on the conditions on both the conditions being satisfied, and that Hume-Rothery rule tells that more will be the size difference. So, more is the size difference between solute and solvent so smaller will be the equilibrium solubility. So, basically that poses a limit because you cannot add large amount of those solutes which have larger size differences. So, basically another and the way what we follow is normally we do that we go to higher temperature. So, you now normally try to get a supersaturated type of metastable solid solution, and so you go at the higher temperature and then quench it, you cool it fast so that you can get it trapped the larger concentration of the solute at room temperature, otherwise which is not possible. So, that is how we also try to have the strengthening by going into that zone where the solubility is more, and then we are cooling it fast or quenching it. Another very this effect of size difference basically will be the apart from these substitutional solutes. So, you have basically there are two things. One is the substitutional solid solution, that is your when your the two atoms which we are using, solvent and solute atoms, they are basically of the comparable sizes, their differences, size difference is not very high. But then you have the example of interstitial solutes, interstitial solid solutions, which are very much this concept is very much used for very very popular type of materials like steel, if you look at. So, in the steel, as you see that we are able to have very we are able to get very high strength because of the interstitial solid solution strengthening. So, as you know that the void, you have the size of carbon which is very small, and it's basically comparable to the size of that void which is there when we talk about the iron matrix. So, in that the way the lattice structure of iron is. So, in that case you will have the two types of voids are there, you have the tetrahedral and you have octahedral voids. So, as you know that when you have the larger solubility of carbon when you increase the temperature, and then when you are decreasing from there. So, when you have the from austenite you are cooling and you are getting the martensite basically. So, basically there again you have the tetrahedral void. So, you have the ferrite in those cases. What you see is that in that case the void being smaller than even the size of the carbon. So, in those case these interstitial solid atoms, solute atom, that is carbon, plays an important role in the strengthening of the steel. And as we know that you are getting very good engineering material in terms of steel, because if you look at the normal solubility of carbon, so it will be about 0.02%. And then it becomes 0.8% at the reactive temperature. So, it is about 40 times the solubility is increasing when you are increasing the temperature. So, that is how you can and then you are cooling it at that temperature highly. So, basically the intense stress field is generated, and then there will be interaction with that stress field of dislocation movement. And so that way you have the effective hindrance to the movement of the dislocation, and that way you are achieving the strengthening effect in the case of steel. So, that is how what you see the effect of these solid solution strengthening in the materials to be very effective, and this is a very important way to have the strengthening in many alloy systems. Now, we will move towards the another effect of that is grain refinement on strengthening. So, grain refinement is basically another way to increase the strength of the material. And what we see that if you talk about the structure of the material or microstructure of the material, what you see that you have the grains, and then grains are separated by the grain boundaries. And when these grain boundaries, because the orientation of the crystals. So, if you look at the grain boundaries, so on the either side of the crystal, the orientation of the crystal will be different. So, basically the dislocation which is moving which is moving on a common slip plane. So, it will be it will be finding difficult to progress so easily. So, it cannot so it will be rarely moving onto the similar slip plane in the adjacent crystal. So, basically that inculcates the one type of strengthening in the in the matter, and it is because of the presence of these grain boundaries and having more and more sites like that means increasing the number of grains in the matrix. So, the strengthening which is achieved because of this is normally called as the grain boundary, strengthening because of the grain refinement. So, what happens that if you look at the electron micrograph of the dislocation piled up against the boundaries. So, what happens that if you see the normal TEM, so you will have basically the if you look at any particular TEM of the alloy, and normally it has been seen that you will have so you will have piling up of the dislocations what you see along these grain boundaries. So, this way what you see, so you will have the piling of, you can see from on these two sides there will be piling of up of these dislocation lines, and that is and also you will have you may have the twin boundary also sometimes what you see. So, in a copper crystal it has been shown that how the dislocations pile up basically against these boundaries. So, what happens that when you have the pilation of these dislocation stationary dislocations. So, in that case the stress which is stress concentration which is there at the leading dislocation. So, when you have so what you can see that crystals are separated by a thin non-crystalline region, that is your grain boundaries, and they will be providing the obstacles to the dislocation motion, and these orientation of the crystals on either side of the grain boundary is basically different and random, and the dislocations are they stopped by the grain boundary and they are piled up against it. So, that is shown normally if you look at the TEM macrograph. So, you can see only at that magnification you can see that how they are piled up against against those boundaries on both the side of the boundary. Now, so what is happening that so this will be basically when you have the piled up area of dislocation. So, the stress concentration which will be there at the leading dislocation. So, your stress concentration at leading dislocation will be product of critical resolved shear stress. So, and that is on the slip plane, and number of dislocations in pile up. So, this way you will have so stress concentration that will be at these leading dislocation, which is this pile up in case of pile up of the dislocation. So, that will be depending upon these number of dislocations that is in the pile up, and this magnitude of this concentration. Now this magnitude of the concentration, it will be depending upon the grain size, as you will see that you will have if the grain size is smaller, so you will have the larger larger pile up. So, I mean when this concentration basically will be the function of the grain size, and grain size being larger, will have these larger concentration. So, in those cases the stress concentration being higher, I mean then you require the lower value of stress to initiate the plastic deformation, whereas when you have the smaller grain sizes, in those cases you require larger stress to initiate that plastic deformation. So, in that line basically there has been a very popular formula which has been given, equation has been given, and that is given by Hall and Page. So, based on his name, this Hall-Page equation basically is suggested, and this equation tells that you have the sigma y is sigma I plus k d raised to the power minus half. So, this is the sigma y is the yield strength of a polycrystalline material. So, it is yield strength of a polycrystalline material. So, for that material the sigma y will be sigma I. So, sigma I basically will be the yield strength of the material, yield stress, this is yield stress basically you can say. So, yield stress of material or it is for a crystal with no grain boundaries. So, basically if you see sigma y. So, when you do not have any grain boundary, you have this is the sigma I, and when you have the grain boundaries, more number of grain boundaries, in that case d will be smaller. Now, in that case this value will go on increasing. So, you have another constant k, and this k is known as a constant. So, from this expression it can be it is quite clear that if the grain size will be smaller, in that case the yield strength will be larger. So, that is what is clear from here. Now, as we see that normally we specify the grain sizes in terms of the number, and it is normally given by the ASTM number. So, if you have the suppose ASTM number n, so ASTM number n means it means the number of grains per square inch, that is per 645 mm square at a magnification of 100x, and so number of grains will be is equal to 2 raised to the power n minus 1. So, this is basically the definition for the ASTM number n. So, if you take this by 100 by 100, so you will have, if you take any area, so you will have the you are doing the magnification at 100 by 100, and that too for 645 mm square. So, if you look at the if you go for the grain size ASTM 1, so it will be 1 grain per square inch. So, 2 raised to the power 1 minus 1 0. So, 2 raised to the power 0, that is 1. So, it will be 1 grain per square inch, and so it will be 1 grain per square inch at a magnification of 100x. So, you will have 10 raised to the power 400 into 100 in that area and divided by 645. So, you will have 15.5 grains per mm square will be basically the size. So, this will be ASTM 1, and if you talk about the grain diameter, so grain diameter will be something like 0. So, it will be 1 by under root 15.5. So, it will be something close to 0.25 millimeter. So, it will be 250 micrometer. That will be the size of the ASTM 1. You can go for ASTM 2, 3. So, every time it will be going by under root 2, like that it will be changing. So, that way you will have the change in the grain sizes, and if you go to larger ASTM, so you will have the ASTM value going from ASTM 1 to 8, and then you can have even for the so then we can have the solution, we can solve the problems based on these numbers, and we can see that how when we decrease the grain size, so how the strength is basically changing. So, that even can be understood when we solve the problems based on that. And there are many ways by which you can do the grain strength, I mean grain size reduction. Many a times we have the microalloyed steels or many kind of steels where we are putting these alloying elements so that they have they form as they work as the heterogeneous nucleating agents. So, they form the nucleation, and that way you can increase the number of grains. So, grain sizes are basically reduced. So, if you talk about the ASTM 14 to 15 size, so it will be something very very small in those cases. So, that way from 250 micrometer it may go to about 2 to 3 micrometer. So, that way you can go in those cases, because 250 and then you have a 2 raised to the power something close to 8 will be that is 256. So, somewhere close to that. So, before that if you come, so it will be somewhere ASTM about, if you take 14 to 15, it will be about 2 to 3 micrometer size. So, if you go, you get very very small, as you go on increasing the ASTM number, the grain size becomes smaller and smaller. So, we will have more discussions about we will have the solution of these problems in our coming lectures. Thank you very much.